So, people are still piling in. We only have 1 hour sessions here at SQLRally, and this is usually a 1.5, 2 hour talk, so I'm gonna speak pretty fast. And I'm pretty sure that your questions that will arise in the middle of the session, I'm hopeful that you will actually get them answered during the rest of the session. So please, no questions during the session, and I'll be available for questions afterwards. I'm supposed to tell you to silence your cell phones. And if you don't know PAST, those of you that are new, there are a lot of different things about PAST, SQL Saturdays, which are free. There are the summit once a year in the US, and so on. So please experiment with all the various offers. So today we're going to talk about high-performance infrastructure, basically a paradigm shift of how we can build platforms for SQL Server. I just want to know, how many went to the PAST summit this November? And how many saw of those of you who did, how many saw my session there? No one. Okay, great, because it's almost the same. My background, I've been working with SQL Server since 4.21a, so that's 21 years this year. And I've been working with Windows ever since the first release of NT back in 1993. And I'm in advisory boards in both Hyper-V, Windows, and SQL Server and Redmond. So I've done a lot, and I usually work in the intersection of those three products. Back in the day, when Gartner moved SQL Server to the leaders quadrant of the Magic Quadrant, they mentioned 3 customer cases. 2 of them were mine, and the last one is American Bank, based on best practices I helped develop with HP. So I'm into motorsports, so I got this little kid's trophy saying thanks from Intel, HP, and Microsoft for making SQL Server do something they didn't realize it could do. But you all here because you know SQL Server has grown up and it does things that it wasn't supposed to do back then when everything was Oracle and DB2. Yeah, so enough about me. So basically, SQL Server, we had a lot of challenges, mainly I/O. And when we go to buy storage for SQL Server, if you ask the storage vendor, they say spend more money and it will run faster. And the more money you spend, the faster it'll run. But the reality is that usually it flattens, right? It doesn't just scale linearly into the sky. And particularly with SQL Server, we actually see negative scale. Because SQL Server is the only relational database out there that spends CPU power converting random I/O to sequential. Oracle doesn't do that. DB2 doesn't do that. Which means the large SAN vendors usually think when it's a scale-up database system, it's Oracle and DB2. So they put an algorithm in their tuning guides for random I/O. But can you imagine what happens when SQL Server comes with a sequential pattern hitting that storage array which expects random I/O? Well, we see a mismatch and we see negative scale. So I have vendors with storage arrays costing millions of dollars that run slower with SQL Server than my laptop. The second thing is, we have this problem about the interconnect. So usually people over-provision their storage. We have the aggregated bandwidth of all the servers that are connected to our storage arrays is a lot more than what we can actually put out of the array. And that also means that our SQL Server batch windows, our runtime during normal business hours, they vary. Sometimes if you run a mail server backup at the same time, it takes longer. If you don't, it's faster, and so on. So we definitely need some interconnect to the storage, which is much, much faster than we've been used to. And this thing about, did anyone hear Mark Sousa's session yesterday? Yeah, okay, some of you. He's a very senior guy in the SQL product group. And back in 2007, I was writing on a white paper to the SQL product group what I thought they should do with SQL Server 2008. And amongst them was a feature that you all know about now, that TempDB can reside on local storage in a clustered environment. And so this is Mark Sousa from a conference a few years back. 2 days before, he was at October Festival in Munich. And this straight American, I think it was a culture shock to see what happens in Europe. And who can trust a guy who looks like that, right? But since he posted it himself, I expected its public domain to misuse it. So the second thing is, so storage array is really complex. Usually when you talk about storage, you talk about the spindles and the LUNs, right? But in the storage array, we have lots of other stuff. We have XOR engines, backplanes, parity, cache lines, port processors, ports, and so on. We also have the fabric, fiber channel switches and so on. But just in the host, we have DSMs, we have MPIO, we have algorithms, we have hotspots, adapters, queue depth. We have a lot of stuff to reach Nirvana. And Nirvana, in my mind, is our CPUs running at 100%. Because if they run at 100%, our storage is balanced, our memory is balanced, and our network is balanced. And if they run at 100%, I need less CPU. And therefore, I need less licensing. And I'm going to get back to how this new way of building SQL Server platforms actually usually pays for itself by just license saving. And those of you who are from Microsoft here, it's enterprise we need, so we still need licenses. And I'm pretty sure that many of you who are SQL Server DBAs have had problems with SQL Server, and you are almost sure it's a storage problem, or you are sure it's a storage problem. But you went to the storage guys, and they say, no, not storage problem, we are only 7% utilized. And if I had a dime every time a storage guy told that to me, I didn't have to work anymore. And if you look at this is basically a heat map of an entire array. Because when you get just one number, it's 7% utilized. They almost always measure down here at the actual spindles. Up here are the ports in our array. Here is the port processors. These big ones are cache lines, backplane, and here we have SCSI controllers and XOR engines that does parity. And these are all the actual drives. And out here we have solid state disks in this traditional array. 0 to 10% utilized, 90 to 100% utilized. So if I had just one measurement, and I'm measuring on the drives on this array, it would probably say 7% utilized. But since these guys are at 100%, I'm never going to get anything more through that array. So fortunately, this was an EMC, VMAX, 11 racks, and you can program it to act differently. So what happened was we ended up with this situation. And that's what we want, right? We want all the shared infrastructure to be balanced. We want it to have lots of room, because usually I can't add more controllers or more ports, but I can add more drives. So I really want my most utilized resource to be the resource I can actually add more of in my storage array. And by the way, this configuration was the storage vendor again being very full of themselves, saying, we have auto-run, auto-rate, auto-tiering, auto-caching, auto everything, so we'll just set and forget it, and it will automatically realize what you're doing. This is us telling the array what we're doing, and we usually get a lot better result from that. Then there are the interconnect. Usually it's fiber channel, right? But it's been installed at 8 gigabit. I know you can get 16 gigabit, but I'm guessing almost no of you are running 16 gigabit fiber channel. And they are even moving to fiber channel over Ethernet. Then we have iSCSI. But iSCSI came from the low end. It's usually 1 gigabit interconnect. If you have 10 gig, it's usually just 2 or 4 links. It's never 16 or something like you can easily do in fiber channel. And then we have network attached storage, right? But I mean, who in the right mind would put the transaction log on a file share, right? Because having copied a ISO file at some point in your life, you have probably experienced some sort of network name no longer exists. And while looking up screenshots for this, I found out that platforms that are supposed to have no faults at all apparently also experience this problem with this. But there's a reason for it. This is the command set for file sharing, right? I mean, how much can you think of doing with a file share? Copy a file, delete a file, modify a file, set writes, modify some attributes. More than 100 commands. There were 14 write commands. Just imagine being a developer. Write 7, write 11, what do I choose? So Microsoft did a good job cleaning it up. 19 commands, 1 write, and so on. The next thing they did, they put in some performance. I'm not going to go deep into that today, but just remember 1 megabyte MTU sizes. So that's basically the packets we can send over the network. 1 megabyte, why that was important. And it was not enabled by default. So this new feature with all the performance, you had to hack the registry. There was no GUI and so on to actually get it. From a SQL Server perspective, well, file shares, 2008 wasn't supported. You could use a trace flag and have it accepted, but not for system databases, only user databases. And if you called Microsoft support, they would just laugh at you on the phone. 2008 R2, it worked without trace flags. It was fully supported, but not for Microsoft databases, only for your databases. So what they're saying is, We don't trust it with our databases. If you want to go ahead and put your stuff there, it's fine, but not ours. So 2 things happened. Back in 2012, we got the Win8 kernel, Windows 2012 or 2012 R2 today, and we got a new SQL Server. And SQL Server was basically waiting. I mean, it came out in April, and Windows came in September of the same year. But SQL Server had some support in there that wasn't opened up until you had the new Windows. And that support was putting databases on file shares, not only your own databases, but system databases, transaction logs. And finally, they actually compared block level storage from a fiber channel SAN with a file share. So now Windows clustering looks upon a file share and says, that's as reliable as a block level storage, or actually more reliable, and I'm going to get back into that. And then with 2012, now you could put tempdb in local storage, so you can basically say, stuff that doesn't have to be in shared storage. I want to offload my limited bandwidth out there. So if I can put a path called t:temp on every node in my cluster, I can put tempdb there, because most of you probably know, but whenever you start SQL Server, it will delete the tempdb files. If they're corrupt, it will create new ones. If you delete them, it will also create new ones. There's no reason to put tempdb out there. And 6, 8 years ago, so I was an idiot. Back then I met Mark Susan and said, hey, great suggestion with that tempdb locally. So coming to what Windows Server 2012 brought to the table. Well, we got InfiniBand, I'm going to get into that. Now finally NIC teaming is something the OS is actually responsible for. How many of you are running teamed network cards on Windows 2008 and back? Yeah, I'm guessing most. It's not supported, but just so you know it. So finally, Microsoft grew up and said, well, Windows 2012 or the Win8 kernel going forward, now teaming is part of the operating system. We don't need a third-party software virtual driver to actually handle this situation. One funny thing, though, is I recently had a customer with IBM servers, and their driver deployment tool for Windows Server 2012 R2 deploys the old NIC vendor driver with the virtual network card and doesn't use the built-in features in Windows. That's a bit strange to take an unsupported solution on an operating system that actually has a supported solution built in. So if you're using IBM servers, make sure that you use the Windows teaming and not the old NIC teaming from the network Windows. And then we got a new version of SMB protocol. But going into the InfiniBand part, well, InfiniBand was usually used in supercomputer environments, and it has a lot of capabilities. But the ones we're interested in, seen from a SQL Server perspective, or for that matter, a Hyper-V perspective, is really, really high bandwidth, very low latency, and something called RDMA. So starting with the bandwidth, well, InfiniBand comes in various flavors, DDR, QDR, FDR, and this has nothing to do with Eastern Germany, by the way. But FDR is the current generation of InfiniBand. That runs at 14 gigabit per second per lane. And then we have lanes just as you have in PCI slots. You probably know you have an X4 slot, an X8 slot, an X16 slot. So InfiniBand can run an X1 lanes, 4 lanes, 8 lanes, 12 lanes. And the most common one is 4 lanes. Running on FDR gives us 56 gigabit per second per port. And since we do 64, 66-bit encoding instead of the traditional 8, 10-bit encoding, we have an effective data rate of 6.8 gigabyte per second per port. That gives a completely different problem, because most servers out there with PCI generation 2 actually has a limit of 3 gigabyte per second in the PCI slot. But just imagine, I mean, I can't remember at any point in my experience in the IT industry that storage bandwidth has been limited by maximum bandwidth of a PCI slot. That's a good place to be, because fortunately the servers you've been buying for the last 3-4 years have generation 3 PCI, and that has enough bandwidth to actually handle this. Going back to the MTU thing, so this is traditional Ethernet, and you see the MTU sizes. Traditional networking is 1500 bytes. That's somewhere around here. So you see, I'm pretty far off my maximum bandwidth of a 10 gigabit NIC. Then you have something called jumbo frames. That's about 9,000 bytes. That's here. That's still somewhat off. So if you remember the 1 megabyte MTU size Microsoft did, well, that's actually what's needed to run at full speed. Up here is the InfiniBand curve. But look at the capabilities, regardless of the I/O size. It's basically a big thresh can, and whatever we pour in, we get maximum bandwidth. Large I/O, small I/O, mixed I/O, we always get full bandwidth. And the thing here in the middle is a hybrid. It's actually Ethernet, but it uses this RDMA capability. And some vendors call it RoCE, RDMA over converts Ethernet. Some call it IWARP. And on InfiniBand, it's called RDMA. So Microsoft, fortunately, has built an umbrella term called SMB Direct. So whenever you read SMB Direct, it's some form of RDMA. But whether it's RoCE, IWARP, RDMA, you don't really know. And unfortunately, those flavors are not compatible. So if your client is running IWARP and your backend server is running RoCE, they won't be able to connect. So you need to make sure that it's the same. But you see that Ethernet gets most of the same capabilities as InfiniBand when we do this RDMA stuff. So basically that means file shares, well, we cleaned up the protocol. We now have what's called transparent failover. I'm going to show you that. The functionality is much bigger. Now we do RDMA, SMP Direct. We have multi-channel. I'm going to show you what multi-channel is. And we have massively decreased the complexity. So if our cluster no longer has any shared storage, it doesn't have DSMs, it doesn't have HBAs, we don't do zoning, we don't do worldwide names, we don't do MPIO algorithm and so on. It's just a file share. So we basically built our SQL cluster, our Hyper-V cluster, and we just point it to a file share and that's it. So it's also a very simple interface to troubleshoot. I mean, I'm sure some of you have had problems with SQL Server and storage in the past. And when it's fiber channel connected, it's usually half years or whole years you spend with partners and vendors and they come in and it's a difficult environment to troubleshoot. Here, I just slot in my laptop. If I can hit the file shares on the back end, those guys are working. If I can't, so it's pretty easy to troubleshoot. Of course, we need Win8 kernel at least in both ends. And going back to this transparent failover. So those of you, how many use Windows clustering today? Yeah, okay, so you know when you move a node from one node to the other, we stop the service, we stop the network name, we stop the IP, we stop the storage, we move it, we mount storage, we start IP, we start name, we do everything. And during that time, 3 seconds, 10 seconds, half a minute, 10 minutes, it depends, we're offline, right? So the new thing they did was saying, well, first of all, our nodes down here, the storage that's behind it is now online on all nodes at the same time. So we're now fully active. The next thing is they got away with the shared IP address. Because if we don't have a shared IP, I don't need to go to the network switches and ping them to update the ARP cache. That also takes time. And so what happens is when you get an SMB3 client connecting to a SMB3 server, it will, while it connects the first time, it will get the IP address of the actual nodes in the cluster. And now we can do 64 node clusters. So if I had a 64 node cluster, this guy here would get 64 IPs. So he starts doing I/O through a file share hosted by this node. And the next thing Microsoft did was saying, well, we need the failover to this guy to be within the timeout of a single TCP packet, which means the network redirector up here, if he no longer gets a response, he now fails over to this path within timeout of one packet. And that means SQL Server never sees that storage is down. And the last thing they did was put the unbuffered write flag on everything. SQL Server does that, Hyper-V doesn't, Exchange doesn't. And I don't know if you know about the unbuffered write flag, but if any of you are using SATA drives, FATA, PATA, whatever they're called, that specification are not supposed to respect the unbuffered write flag. That's why I'm guessing if you ever had a corrupt database, I'm 99% sure it was because you didn't use SCSI or SAS, but you used SATA or PATA or something like that. Because it will actually, it's allowed to store IOs from SQL Server in its own local cache on the drives, but commit it to the software, and it will commit the transaction. But imagine if power is lost, well, that's gone. Whereas the SCSI protocol says, if the IOs comes in and it has the unbuffered write flag, I will respect that, I will write it to stable media that will survive a power outage. But what they do here is whatever I/O comes in, they don't even check it, they just put the unbuffered write flag. Because if this node goes down, we can't really allow that the host memory has some of our data. We need to make sure that the data is written down here. But those three things together means I can start SQL Server, do I/O, 500,000 IOPS, I'm going to show you that later, per second, go down to the machine room, and I can pull the power plug under my active node, and this guy here will resume the I/O without SQL Server ever noticing it. If you did that on a clustering today, that database, if it lost its storage, would become gray, suspect, and offline, and some DBA need to go in and save the day, right? And that means we can actually do unplanned failures, and that's 100% uptime. This is just not 5 nines, this is 100% uptime. That's pretty good. That was the goal for the Win8 kernel, to say, Microsoft hated that whenever something needed to have an uptime, people will say, buy a mainframe, go to Linux, because Microsoft is not high available. Well, now for 5 years, we've had code that are 100% uptime. I can do unplanned failures in the middle of production. I can just pull the power plug on my active nodes, and I will have no outage while doing it. So back to multi-channel. Well, networking had that problem. I'm sure some of you have tried copying a file from one server to the other. You know the bandwidth is maybe 100 megabytes per second. You know you can read and write with at least 100 megabytes per second. But that file copy runs at maybe 27 megabytes per second, which doesn't make sense, right? It should run at 100. But the reason being is that it used to be so that a data stream on TCP on Windows could only open one channel. And that channel could actually saturate a core on a CPU. Because remember, our CPUs are getting slower, right? I remember we had 4.4, 4.6 gigahertz CPUs. And today, if you buy a new sexy server, it's 2.2, 2.6. So we almost halved the clock speed that we used to be. And unfortunately, that code was single-threaded. And if my cores are now half the clock speed, well, actually a 10 gig network card can saturate that core on a current generation CPU. So that's not good. So the new thing is, since Win8, or Windows Server 2012 and forward, we can now open multiple lanes, and those lanes are all redistributable on all the available CPU cores. So a single core is no longer a bottleneck. And we can open up to 8 lanes per NIC. The next thing is, well, sometimes you need teaming, and now that's built in, that's fine. But if we just use it as a storage interconnect, maybe I don't need VLANs and every kind of all advanced setup. I just want extra bandwidth. And that's where multi-channel comes in. That's basically automatic teaming. So what happens is, when the client connects to the server, it will query this guy and say, hey, you are SMB3 like me? Can you give me a list of all your NICs and their capabilities? And he will discover saying, I have a NIC on the same subnet that you have. So instead of just running on this guy, let's do this. So we open channel 1, 2, 3, 4, 5, 6, 7, 8. That's pretty smart. And I can add a third one, or a fourth one, and a fifth one. And in the test we actually did in the lab in Redmond, up to 12 network cards. And it scaled linearly. And that's actually an example here. So this is 10 gigabit Ethernet, one port, 1 gigabyte per second, 2, 2, 3, 3, 4, and 4. And we did that up to 12, and not because 12 is the limit. That was just the biggest server we had. We didn't have more than 12 PCI slots available. But imagine this is InfiniBand. 7 gigabytes per second, 14 gigabytes per second, 21 gigabytes per second, and 28 gigabytes per second. 2 cards, 4 ports, 2 PCI slots, 28,000 megabytes per second bandwidth. That's a lot. And even those fancy NAND flash array vendors out here who are proclaiming, and they, with rightly so, are the fastest arrays in the world, they're nowhere near 28,000 megabytes per second. So finally, we have an interconnect for storage that is so fast that, like Bill Gates said at one point, 640 kilobytes is enough for everyone. I'm gonna risk and say, this is an interconnect. And imagine we put in 12 of these cards with 14 gigabyte bandwidth each. This is an interconnect that's going to be enough for the foreseeable future, right? So back to the RDMA. You probably know DMA, Direct Memory Access, where a user mode application can access the memory space of a hardware device. R in RDMA stands for remote. So it's basically the user mode application on one server can access the memory space of a hardware device on a different server. So what happens is that the application, again, SQL or Hyper-V, goes to the network redirector. It figures out we are RDMA, so that's Microsoft term, SMB Direct. So we bypass locally the entire TCP stack. And because everything is in silicon in InfiniBand compared to traditional Ethernet, I can move directly down here. And this guy over here, he can access the memory space of whatever it is I want. For example, it could be a direct attached Fusion IO card or something like that, bypassing the entire NTOS kernel on the different server. So in one of my examples, you'll see I'm putting massive amounts of IO, lots of data, and the CPU is at 1%. Because we never want to scale these guys. We want 2 for a cluster and maybe 3 for n+1, right? If one breaks, we are still resilient while we fix the first one. But we're not going to put in more nodes for performance. How it works is the initial connection is our traditional TCP/IP. When it figures out it's SMB direct, it moves to that protocol instead of TCP. But it keeps the TCP open. So if for any reason this protocol should fail, it will transparently move back to TCP/IP without the RDMA, again with no outage. A bit like if you used ISDN back in the days, there was those 264K massive data pipes to the internet. And it had a 9K D channel also, right? And that was, and if you knew that was always online, and they didn't meter it, at least here in Denmark they didn't. So if you only had 9K, you couldn't move your data across the metadata channel and leave the metered ones alone. But it's basically the same what happens here. And going into why is this so important to get it so fast? Well, this is Jim Gray. Some of you probably know he used to run Microsoft Labs, was hired back in SQL Server 7. Now he's gone, he disappeared. He went out on his yacht, and we never saw him again. The yacht was never found, and I don't know what happened. Probably didn't like his wife, bought an island, and turned off the systems that were supposed to automatically send distress signals. But he has this idea saying, well, in order for my brain or the transistors in the CPU to actually do something, I need it to be in memory. But the closest memory to the transistor is the register. And that's the same as for my brain to my spectacles. But in order to put it in the register, it needs to come from cache. That's basically from my brain to my desk. But in order to move into cache, it comes from main memory. Well, that's my house in the attic, in the basement. But in order to fill it into memory, I need to go to storage. And with our traditional storage mechanisms, our traditional interconnects, in that perspective, it's like traveling to the moon. So you can probably realize that if I need to go to the moon very often, I'm not going to put my CPUs at 100% very often. And I'm also expecting that when your users call in the hotline saying, it's running so slow right now, and it's our biggest peak hour, and you log onto your SQL servers, and they are probably 8-12% utilized in the CPU, and again, well, we have enough capacity, right? But the reason being, well, I can do a little CPU, then I wait for ages for I/O, do a little CPU, and again wait for ages for I/O. But what if I have an interconnect that connects storage that is as fast as memory? I'm going to show you an array that does 6,000 megabytes per second. That's almost the same speed as CPU to its local memory. And if I have the InfiniBand link that has more bandwidth than CPU to local memory, well, I can do this. And if I can do that, I can have a reduction of servers. There's an example here, a customer with 4 full blade enclosures and a VMAX. They moved to a NAND flash array in this modern sense with fast interconnects. And we can now actually run the same workload on just one rack. That's 75% reduction in licensing, 75% reduction in servers, acquisition, patching, backup, and so on. Cooling, power, rack space. So this leads us up to now we can build our own stuff. So we could basically just take a file server, put in some PCI flashcards, and that's it. But some of you will probably say that's a single point of failure, and that's where this new transparent failover cluster comes in. So of course it requires we have shared storage that all the nodes in the cluster can see, but these guys are now 100% uptime, and that's probably more than most SAN vendors can say. We could also put in Hyper-V. It also supports this, and that means we can virtualize everything, or actually have everything run on this interconnect, because it's only SQL and Hyper-V that supports this. So if you have an old version of Windows, or you have an Exchange server or something like that, well, if you run it inside of Hyper-V, you could use the same infrastructure to solve problems there. And that's actually a good argument, because NAND flash has 2 capabilities that traditional storage doesn't have. First of all, it's 100% fragmented. So it doesn't care. If you don't fragment your data, the professional enterprise-grade NAND flash will do it for you in order not to wear out the NAND flash cells. And that means all of a sudden you don't have to make all these LUNs saying this LUN is for SQL transaction log, this is for tempdb, this is for my exchange servers, this is for that, because and this can't use the same physical spindles and this, because if I do, we'll have an overlap and they'll do random I/O and it'll be slow. Here, we don't really care. We'll just put in everything in a big chunk. So we also see a much simpler operational perspective, because instead of doing 50 or 100 or hundreds of LUNs of all various sizes, because the business says, well, I need 100 gig, I need 200 gig, I need 50 gig. And usually they're wrong. Those who say a little needs more, and those who say a lot doesn't need it. And I'm guessing you probably have wasted storage islands everywhere in your storage. What we do here is just we make massive LUNs, 10 terabyte, 15 terabyte big LUNs, where we just plow in everything because we don't care about fragmentation. And another reason about NAND flash, the second capability, is that random I/O is as fast as sequential. It's just memory addresses. So it doesn't matter if we plow in everything together. And all of a sudden, our storage provisioning is no longer logging into a storage array, which we don't do that often, doing worldwide naming, doing zoning, logging into Brocade switches, and so on. Now it's just log into Windows file server, create a folder, right-click it, and share it, and you're done. That's your storage provisioning. And those folders live in the same big LUN. So if that LUN for application 1, who said we needed 200 gig, only uses 50, well, it only uses 50, like a folder in a file system. So we have free thin provisioning. We have no overhead of all these things. So we actually only need storage that is what I would call pretty dumb. We don't need all these advanced capabilities because Windows now has all the advanced capabilities. And to show you some interesting stuff, I do some I/O here. If the demo guards will, and usually they do when you record your demos. So it says drive 1 colon. It's just because it's disk 1, I didn't assign it a drive label. It could have said F colon. I'm running for a minute. I'm gonna do reads, 0% random, and these numbers here means, and you will see that down here, that we will run 64K I/O. That's the most common I/O size that SQL Server does. And when we start, this is a Fusion I/O card, and that's limited at 1.5 gigabyte per second. And that's more or less what we do. You see 65K or 64K, and look at the latency, 0.000. But I'm also, it's local storage, right? And we're running. But look at the numbers, 1483, 86, 83, 85. Can we agree, we're never above 1500, right? Just below 1500. And when this is fit, and see the CPU utilization, right? And when this is finished, just skip to the end, you will see that our 64K I/O took 309 microseconds. All storage vendors always report latency in 4K I/Os. I have no idea. I know of no application that does 4K I/O, but it gives massive amounts of I/Os and really low latency. So imagine you divided this by 16, you would be in the, I don't know, 30, 40 microseconds for an I/O. That's pretty good, right? 2-digit microseconds for an I/O. That's approximately 1,000 times faster than your traditional array. So moving on, just one more point. I'm using physical disk. Never ever use that. When you use performance monitor, always use logical disk. But look at the counters. Average disk bytes per read, bytes per write, second for read, reads per second. Those of you who have been looking at network counters before, you needed a Caltech diploma. And even if you had one, you would look at it and say, what? They really grew up and say, now we have these client shares, and look at the naming. Second for read, bytes per read bytes per second, and so on. So again, all the way through, Microsoft now look at a file share as block level storage. And when we start disk 1, if I can find the mouse here, you can see the difference now is whack server name, whack share name, and a file. All the other parameters are the same. But look at the numbers. 97, 1560, 1510. That's pretty impressive, right? 1519. I just did a platform at a customer, and their the vendor of, I don't sell hardware or software, but their vendor of hardware, they put the senior architect on, and he looked at my design and told the customer, and I have the email, it's pretty, I should put it in the slides actually, because he wrote, "Dear customer, if you want really, really, as in, and then parentheses, really, really, really low latency, you need to strip away the file server layer, because the fewer layers you have, the faster it will run." Well, and look at the microseconds. 309 before, 303 microseconds. So it's not a lot, but can we agree it didn't get slower, we didn't get more latency, we get less latency, we got more bandwidth. And actually, this is R2, the WinBlue. Back in 2008, the Win 8 kernel, we actually saw up to 30% difference. That local storage, if I moved off-site to the second server with this infrastructure in place, I saw 25-30% performance boost on mechanical drives by putting in an extra layer. So I think this is pretty good. The next thing I wanted to show you is just to give you an idea what's actually possible over file share, because if you look down here, just to get an idea of the IOPS, can it do big IOPS? Well, 534,000 IOPS per second. Is that okay? How many has a storage array that does more than that on traditional fiber channel? So it really is high performance, and it really is grown up. And to show a little bit about the continuous availability. So what I have here is a server where I have two links to show it, and they are on top of each other. I'm just going to skip configuring iometer, but I'm just going to set up some reads. And once we start that, you can see up here we are running on the file share, right? And when it starts, we should see I/O go up. And it's a little bit difficult to see, but here I'm actually swapping between the two network cards. And so you can see they are exactly on top of each other, 50-50 shared, right? So what I'm going to do is I'm going to introduce a failure. Here. And I'm going to do that by disabling one of the network cards. If I did that before RDMA and this stuff, iometer would explode. And it's open source. So you see here, right-click, disable, and see what happens up here. One NIC goes to double, and the other goes to 0. But iometer, those of you who use it, the tiniest outage of I/O, it will explode, and it will start drawing error boxes, you know, in vertical lines across the screen, because it doesn't really have a great error handler. It's more finicky than SQL Server is. So let's try and fix it. And again, if the demo guards well, we should see that once we enable this guy, it will figure it out, look at it's available, and redistribute the data again. So we're once again highly available. That's pretty cool. This is an unplanned failure and no outage to the application. And just quickly about virtualization. I'm guessing also that most people want to do virtualization, but a lot also say, well, you can't virtualize SQL Server, especially if it's big. So the biggest challenge is basically I/O and do fast I/O. So on the Win 8 kernel, the Hyper-V 3 release, Microsoft wanted to be the best hypervisor in the world for SQL. And the way to do that was to do high IOPS workloads. And how do you do that? Well, this was Microsoft's original idea of the space to do, the servers out there, 4 CPUs, that was maximum. And Hyper-V version 2 could already do for 4 CPUs virtual. So why on earth do anything more? At that time, I was working for a company where we did a IT reporting, BI solution, and we were scanning a bit over 13,000 servers every night. But if we dug into those and took out just the ones that run SQL, we were looking at about 1,600 servers, 2,300 instances, 10,000 databases, 6,000 CPUs, 15,000 gigabytes of memory. And the picture is different. So if we want to do grown-up SQL virtualization, we need a lot more CPUs. And the second thing is that once we do that, we also, when we start to do big ones, we see storage savings. And I'm going to get back to why we see that. So in version 2, we could do 4 CPUs, 64 gig of memory. In version 3 and forward, we now do 64 CPUs and a terabyte of memory in a single virtual machine. That's more than VMware does. And look at the host, 320 processors. I mean, AMD is no longer interesting, and Microsoft develops everything on Intel. But at that time frame, 10 cores was the maximum. So if we take up higher threading, it says 160. If we divide that by 10 cores, it says 16 sockets. I don't know about you, but how many 16 sockets Windows-capable servers do you know? But that was a prototype system they had, and it actually had 32 sockets. So 2 weeks before release of Windows Server 2012, it said 640. So Dave Cutler actually scaled the Windows kernel to 640 CPU, and the SQL Server team scaled SQL Server to run at 640 CPUs. He also had a prototype with 64 sockets. That's 1280. Task Manager looks really funny with 1280 processors. But the SQL Server team hit a limitation. They knew what it was, but it was a major rewrite and said, well, for the time being, 640 CPUs is probably enough in a single instance. I don't know about you. So pretty big numbers, right? But we still needed I/O. So what happened was, just before TechEd, VMware came out with 300,000 IOPS. And that was the biggest number ever on a virtual machine. 2 weeks later, Microsoft at TechEd announced 1 million IOPS for a free hypervisor. I think that's pretty cool. So 1 million IOPS, 1 terabyte of memory, 64 processors. How many of you have larger SQL servers than those? Yeah. So it really is possible now to do grown-up SQL virtual. So going back to the storage performance, since these NAND flash vendors really try to push random I/O very, very fast, sometimes they forget sequential I/O. And I was just recently at a customer with a dedicated NAND flash array. It ran at 1.6 gigabyte per second when we did random. When we moved to sequential, which again, you know, SQL Server does a lot, it fell to 40 megabyte per second. Because the only focus they had was do really good software encoding and algorithms for random I/O. So when you put a sequential application in front of that array, it just fell apart. So if you're going to test NAND flash arrays, make sure you don't just do what the storage vendor asks of you in your proof of concept and test random I/O. Make absolutely sure you pay a lot of attention also to sequential I/O. But this is an array that does almost, you see, 6,000 megabytes per second or 6 gig per second. This is random. Moving to sequential, we see a bit more, but approximately the same. That's what I would expect of a good, well-developed NAND flash array. And so far, in my experience, I've only found 2 vendors out there that does that. And I've tried a lot. But that's on the file server, right? Or you see logical disk. Now, if I move to the Hyper-V node, and I see client shares, well, look at the numbers. 5,900. It was just 5,700. So again, I get a boost in bandwidth by adding this extra layer, plus all the extra capabilities, the simpler setup and so on. But what happens if we move into the virtual machine? What's the overhead, right? Well, doing a virtual machine, doing the HDX files, so now it's again a logical disk, but in reality that logical disk is placed on the file share. 5,930. So I lose 6 megabytes per second out of 6,000. That's pretty okay, isn't it? That's an overhead most can live with. New things are happening, have happened actually. So we have SQL Server 14, we have that for a while. We also had R2 for a while. Some of the things in SQL Server is mainly focused, let's take Windows first. They did some rewrites. So when VMware caught up with 1 million I/O, now Microsoft on the same hardware, if you just upgrade to R2, it does 1.3 million on the same hardware. My first customer, where we in-place upgrade the server, we went from 950 megabyte to 1.3 gigabyte per second, same hardware. So that fits Microsoft's numbers pretty well. There are some new interesting stuff coming. It's not really interesting, and unfortunately most Microsoft salespersons and key account managers, they mix up what I've just shown you with the transparent failover and the scale-out file cluster. They mix that up with storage spaces. So whenever somebody from Microsoft talks about storage spaces, you just shut down your ears and think that's a system for non-high availability. It's for single site. It's not about really professional installations. But they mix that up very often. But you really want the scale-out file server and the transparent failover stuff. Just not the storage spaces yet, because it's really interesting and some good things are coming in Windows 10. On the SQL Server side, well, most of the new stuff in SQL Server is mainly about in-memory stuff, right? You've probably heard on this conference in-memory OLTP, updated clustered column store indexes and so on. And if you talk to Oracle, you get Exadata, and with SAP you get HANA, and everybody talks about in-memory, and they usually also say forget about storage. But let's dig into that a little bit. So imagine I wanted to use in-memory OLTP. Well, if I had a web shop and my users put something in my shopping basket, if that server broke, it's okay. He has to put that stuff in the web basket again, right? But what if I was a bank doing money transfers or a telco doing CDR records for billing? I don't really want to lose that data. So in memory OLTP, you can implement either just the schema is persisted on disk and the data is volatile. But I'm guessing most of you like your data. So I'm going to persist my data to disk also. And can you imagine this fancy in-memory technology, how fast that runs if I persist my data to a slow disk? Probably the disk speed, right? And going to the column store indexes, well, now they are updatable. And so when you build it, it's fine, it's in memory. But what happens with that delta store where we do the delta parts? Well, let's persist it to storage. So that runs again at disk speed. So most of these memory technologies really doesn't make sense, except you're in a keynote. And I just discussed it with Mark Suse the other night, saying, you do so many new features that do fantastic keynotes that nobody really uses in real life. And I don't know if you have the same opinion. How many uses in-memory OLTP already? Because you need to reroute most of your code. Yeah, that's it. 2 out of, I don't know how many is in here. And if I went under NDA, I could start talking about SQLV next. And yeah, well, I had a long discussion with Mark Suse, and I have a different opinion of some of the features. Another thing is, well, this is the traditional way of thinking, right? So NAND flash and mechanical drives is storage, DRAM and cache and registers are memory. But since DRAM is running so fast today, NAND flash is running so fast today that it's at DRAM speed, maybe we should shift our perception and say that's actually a memory technology. It just has this interesting feature of data being persisted if you lose power. And so we could call level 4 cache and level 5 cache. So what Microsoft did in SQL 14 was called level 1 memory and level 2 memory. And the way they implemented that is, so inside a SQL Server we have the buffer manager. He's the only guy inside a SQL Server who can touch storage. If some part of SQL Server needs data, it goes to the buffer manager, he looks in the buffer pool, is it there? If it's not, he fetches it from this, puts in buffer pool, and puts the pointer up here. So since he's the only guy knowing about memory, well, it was interesting and very easy to call this the level 1 buffer pool. Add in some NAND flash that's really fast. It could also be shared, doesn't have to be direct attached, and call that the level 2 buffer pool. So SQL Server tags every page it's using. How often? What's the hotspot pages? And the hotspot pages stay in buffer, the rest is on storage. But now that we have a second level buffer, that's almost as fast. Well, then the really hotspot pages is in DRAM. The normal hotspot pages is on that NAND flash device, and everything else is out here. So imagine this is a standard edition SQL, and you have 128 gigabyte limitation of memory. Well, I can put in 6 terabyte of NAND flash. And so that actually boosts my standard edition pretty well. And fortunately, it's a standard edition feature. It's pretty easy to enable, just a single command. And it's fully integrated to DMVs, XEvents, performance counters, and so on. It actually works like memory. It's completely transparent to the application. Then another thing that's interesting is, well, we had this resource governor for a while, and we can govern memory usage and CPU usage. But going back to the discussion about, well, a really heavily utilized SQL Server is probably almost never at 100%, right? So how great is it to do a resource governor policy of something that's never 100% utilized? It doesn't really make sense, right? So the new thing that appeared in 14 was, well, the resource that is always utilized a lot is I/O, and now we can finally do that. So that's pretty important, I think. Going back to that storage saving, well, we looked at a customer who had 750 SQL servers, 920 instances, so that's a pretty good statistical basis. But it turns out of all the allocated storage, 37% was system databases. Because when I have 920 instances, and they bring in 4 system databases for every single little small database I get. So this is just massive amounts of savings I could gain. Of the last 63% that was actually allocated to data files and transaction logs. Well, digging into that, it turned out, well, the file systems were only 57% full of data files. Looking into the data files, they were about 1/3 full. So 83% of the 63% is wasted space, and most of those 37% is also wasted space. So that again says, when you have this SQL sprawl and you have hundreds of SQL servers, it's impossible to reclaim your storage and really get a good utilization of your platform. But if you start to do great consolidations, you move to a file share-based storage backend where everything is just folders in the same big LUN, you don't get all this waste. You will utilize every single bit of your storage. And if I can reclaim almost 37% plus 83% of what's left, well, maybe I need to buy so smaller storage that it doesn't really matter. It's more expensive than what I normally pay. This was another way of looking at it. Virtual files, SAN files, direct attached storage. But they had 333 gigabyte of SQL Server data running on USB drives. So I'm guessing some servers all of a sudden ran full, we plugged it in and forgot about it. And again, with 920 instances, of course you're going to forget stuff. You're not going to patch stuff also, right? The CMDB, well, we found 156 servers that didn't know existed. But looking at what they thought they were running, these are all servers running SQL. I think this was pretty funny. They had 3 servers tagged as DB2, but they were actually running SQL Server, so they've been migrated long since. And a really good thing about this platform is finally, something we haven't been able for many years, is now we can brute force bad code with hardware. Right? So if we go 5-6 years back, if we bought a new server, our crappy code ran faster. But for the last 4 or 5 years, if you buy a new server, it runs at half the clock speed, it's single-threaded code, it runs slower, right? So buying new hardware doesn't accelerate anything. So take this simple query. It can produce interesting query plans. And those of you who are used to query plans knows that usually these guys means this is a break. This is a speeder. This is a break speeder, break speeder, break speeder, break speeder. I think this is a really beautiful query plan of columns of stop and go. So this was a customer saying, we're really good at writing code. I said, let's look at the query plan. He saw this, we explained it, and I said, can I get a picture of that and use it in my presentation? Because I think it's really beautiful. And he wrote in the subject, how not to write SQL. But in order to make that, the reason that this runs so bad is this, right? This is something you probably see a lot. Lots of threads, they're all suspended, and the reason they're suspended is CX packet. So CX packet is not a problem by itself, it's just a way of showing there's a problem with parallelism. It's a synchronization mechanism weight that something else is wrong. The right thing to do, right, of course, is to have your developers learn about indexing and partitioning and querying so that this doesn't happen and really understand parallelism. But it appears nobody wants to learn about parallelism, except today we run a server that has 160 logical processors for a 4U server. We really need to know about parallelism. The next thing would be to go to Microsoft and say, take that stupid query optimizer and make it do parallel code right, instead of us having to do it. But it seems it doesn't do great keynotes to do that. It's better with cartoon characters. So we have to do it ourselves from the DBA side. And what can we do? Well, we can, how many know who Thomas Kaiser is? He's a good friend of mine, yeah. This is an example of his way of hacking that simple query we started out with. Now it runs parallel, except for one little problem. This trace flag, which is needed, you have to be local administrator on your SQL server. So if this was code running on my website, for example, all my anonymous users needed to be local admin on my SQL. So I'm guessing that's not a really good idea. Then the next thing you could do is make it even worse. And you see, we cross-applied with this function. That's a good guy called Adam Mechanic. Anyone heard of him? Yeah, he's pretty smart. He never worked for Microsoft. But somehow, what Microsoft in the Query Optimizer team never figured out doing, now 21 years since it was first released, from the outside, he reversed engineered the logic inside of the Query Optimizer. Made this, and the reason I cut it here is because it's a really long array, and said, if you just take your code, make it really crappy like Thomas Kaiser said, and cross-apply it with this stuff, it runs parallel, and you don't need to be local admin. So if we can hard code wrap the same thing about every single code, why on God's green earth can't the Query Optimizer team do the same? I don't understand that. So we're basically left with one thing, right? It's brute force. Buy new hardware. And whenever I meet a customer and say, well, we're going to do this new SQL platform, and we're going to buy this great new server, lots of CPUs and lots of memory. And I ask, well, what about storage? Well, storage, oh, we're just going to connect it to a traditional array. A communist system, as I call it. The platform that is supposed to handle everything, small and big. Usually, most are aware that if we do a little bit different with storage for SQL Server, it will work better. Then we have the developers who might be a problem. We also have IT admins who use old best practices. But what I'm advocating is, maybe we should buy the Ferrari. Let's buy storage that is a lot more expensive than we used to. But the problem is silos, right? We have a server silo, we have a storage silo, we have an application silo. They have individual budgets, and the storage guys don't have the money to buy more expensive storage. But actually, it turns out that the licensing, what if I can decrease my SQL licensing by a factor of 8? Well, that turns out to be a lot of money. So most of these customers actually finance that more expensive storage by reducing licensing cost and server acquisition. But we need to get rid of the silo stuff. So instead of being individual budgets, we need to look, build a roof on top of all the silos and think, this platform stack, the total budget in networking, in storage, in servers, in licensing, in management, is usually lower on this kind of Ferrari storage than it is on traditional storage, because we need many more servers, many more licensing. I had a customer, an investment bank. We went from 60 servers to 2, and every single application ran faster, and the entire platform was financed the first year by savings on everything else. But I'm not saying go back to this, right? Not one man by building everything. We've been there in the IT business. It turned out to not be a good idea. So this is a customer of mine where we did a proof of concept, and now they actually bought the platform. But the current system ran about 500,000 records per second in development, and a bit over 600,000 records in production. Just migrating to this new kind of storage platform and nothing else. The same code, we didn't optimize anything, we didn't use any new fancy features. That moved 13 million rows per second. Because now we have storage that is 1,000 times faster for latency than what we used to have. And that turns out to give us an increase of 21x. Not 21%, but 21x improvement in query performance without rewriting a single line of code. So we had a break of 5-6 years where we couldn't brute force bad code with hardware, but now we're actually able to do that again. And development, of course, a little bit faster. Then just for the fun of it, we put out a clustered column store index on it, because now that it's updatable, well, we can start using column store index for a lot more than we thought about. I mean, that used to be a niche BI feature, but it's slowly maturing, right? And putting a column store, deleting all indexes, putting column store in, improved it by another factor of 16. So 21 times 16 actually meant the queries ran 330 times faster with no code changes and simpler indexing. And 472. And because it's a clustered column store index, I also needed almost just 1/3 of the storage that I used to use. So 2/3 of my storage cost was just blown away because I don't need the storage anymore. Now I have clustered column store. And one other thing about virtualization, attention to details, not only in the physical world, is really important. So this is an example of a virtual machine deployed on Hyper-V, doing networking. It's a 10 gig network card, and you see we do 550 megabytes per second. Next, finish. But setting one check mark in the guest, not in the host, One check mark in the guest made it to 740 megabytes per second. And something that's off by default. So again, it's just to show that the hardware that's out there has some capabilities that the software can, but because some might be afraid for regressions, we don't enable it by default. So it really pays to say, if we want to do high-performance SQL and we want to do it virtual, we need to pay attention to details. Because I got a comment after one of my sessions some time back saying, they went out and bought into this and they just bought some equipment and put it together and they didn't get an effect. Well, maybe Google is not the right way to do it. But it is really simple. Once it's built by the right components with the right settings, it's a really, really simple day operation. And the feature we used is something called VMQ. There's another, even more advanced feature where you can actually expose a physical network card directly inside of the guest. So you no longer have virtual network card. If I have a Mellanox network card in the physical host, now I need to install the Mellanox drive inside of my guest. And that runs at full wire speed, 1.1 gigabyte per second. And I can even team them, so I can do 2.2 gigabyte per second bandwidth out of a virtual machine. I think that's pretty cool. So new things on the road. This used to say SQL Server 15, but since it's not coming in 15, and people tended to put an equation between 2015 and SQL 15, they moved it to a different naming. So it's called SQL vNext. And I'm guessing it's probably been 16 the release, but I don't know about that. Then we have Windows 10 coming. And some of the new features that I can show you is about the storage stuff. So here I have an array. Actually, I have two arrays, and I have a synchronous mirror in software. And you saw it earlier, I did about 2.7 gigabyte per second. We're just going to start the iometer. And once that's running, we should see that this synchronous mirror has no overhead whatsoever when we write it. And let me just here. So again, you see about 2.8, 2.7 gigabyte per second. No overhead whatsoever. So the only thing I'm going to do is I'm going to go into iometer, and I will change from, let me go back, from writes to reads, and something magic happens. Well, good rate controllers does something called split seek. That means in a mirror, I know that I have the data twice. So instead of just reading from one half, I might as well read from this half, then this half, then this half, then this half, and get the effect. And see what happens. Almost 5 gigabyte per second. So that's pretty advanced, right? Now my secondary array in the second data center that are synchronously mirrored and used to wait for the first one to break down and just basically burn off power and cooling. Now it's actually helped me. In normal operations where everything works, this helps me out. I have almost twice the read, and usually, I mean, I'm guessing most of your databases is more read than write. So my copy center helps me out in daily operations. It's no longer just something that's sitting there waiting for the first one to break. I think that's pretty cool, right? So that was it. There should be some paper somewhere to fill out evals. And if you want to contact me, well, find me on LinkedIn. I also put my Twitter up. When you talk at a conference in the US, I don't really use Twitter. I used to not use it. But you can't actually navigate an American conference anymore if you're not on Twitter. Everything's on Twitter. And I got this guy saying, you need a cool Twitter name. And he figured this one out. So maybe connect, and I'll try to use it more than I used to. But contact details are on LinkedIn. So that was it. And if you have any questions, just come up afterwards.